The center of mass examples that we've looked at so far, where we've used integration, have been things where we've had a uniform density. We had a uniform mass per length, or a uniform mass per area, or a uniform mass per volume. Now we're going to look at a simple example where we have a non-uniform density. Here we have a rod that has a non-uniform mass per length. And in these situations where you have a non-uniform mass per length, you would need to be given how that mass per length changes with position. So this is something where the mass per length lambda is a function of x. This says that lambda equals a times x squared. As x gets bigger, lambda gets bigger. So the way you could think of this rod, maybe it's made of a styrofoam and concrete mixture. And on the left side of the rod, it's more styrofoam. In the middle, it might be kind of a mixture of the two. And on the right side of the rod, it might be more concrete. And so as you're moving along the x-axis, it's getting more and more dense. That linear mass density is getting bigger and bigger and bigger. The way that we calculate the center of mass for something like this, it's still the equation 1 over m times the integral of x dm. So one of the things that we need to do is we need to figure out what m is in terms of a. This quantity a is related to this mass m. So we're breaking this rod up into these little tiny pieces dm. The mass of those little tiny pieces is lambda times dx, the mass per length times the length of the little segments. But we know that if I integrate from 0 to L, all of those little pieces, if I add all of them up, they need to add up to equal that total mass m. So if I add up all of the little tiny pieces dm, those have to add up. Again, an integral is an infinite sum. These pieces dm have to add up to equal the total mass m. And those little pieces dm are lambda times dx. They have a mass of lambda times dx. So m, the total mass m, has to equal the integral from 0 to L, from the left side of the rod to the right side of the rod, of lambda ax squared times dx. The integral of ax squared dx is ax cubed over 3, and we're evaluating it from 0 to L. And so that becomes al cubed over 3 minus 0. And so then I can rearrange and solve this for a, and I get that that constant a has to equal 3m over L cubed. That constant that's there must be 3 times the total mass m divided by L cubed, so that when I add up all of the pieces of this rod, I add it up to get my total mass m. So now we're ready to look at calculating the center of mass. The x coordinate of the center of mass is 1 over m times the integral of x dm. But again, dm was lambda times dx, so this is 1 over m times the integral of x times lambda dx. But we can substitute in lambda. We know that lambda was ax squared. So we have 1 over m times the integral from the left end of the rod, x equals 0, to the right end of the rod, x equals L, of x times lambda, ax squared, times dx. And so now this is something that is all in terms of x. I can bring the a out in front of the integral, so I have a over m, and it's the integral from 0 to L, x times x squared is x cubed, so it's the integral of x cubed dx. And the integral of x cubed dx is x to the 4th over 4. Evaluating it at 0 and L, I have L to the 4th over 4 minus 0 to the 4th over 4, which is 0. So I have a over m times L to the 4th over 4. And this is why I needed to find a in terms of m, so that I would be able to simplify this. A, we found previously, a was 3m over L cubed. So I can substitute that in. It's 3m over L cubed divided by m, that's a over m, times L to the 4th over 4. And so the m's divide out. I have L to the 4th divided by L cubed, which just leaves me L. And so I get for my final answer that the x-coordinate of that center of mass was 3/4 L. Again, if this was a uniform rod, the center of mass would be at its center, halfway between the ends at L over 2. This is something where the density was getting bigger as I moved to the right. This center of mass had to be to the right of the center. And this is 3/4 L is over somewhere on this right half of the rod. So things with non-uniform densities, it's not any more difficult. You just have to substitute in lambda in terms of x if you have a non-uniform mass per length, or you might substitute in sigma in terms of area. If you had a non-uniform area density, that would be a little bit more complicated. That would involve a double integral. But the most common one in introductory physics is having things like this with a non-uniform mass per length, where you're given lambda as a function of x. The concept of it is exactly the same, that the center of mass is 1 over m times the integral of x dm. The only difference is this dm, which is lambda dx. This lambda is a function of x, and so we need to include in that functional relationship.